Okay, so we are going to talk about gauge transformation. But here we have talked the gauge transformation for the diffeomorphism constraint and Hamiltonian constraint is just the same as before. So here something new is just Gauss constraint. Okay, so let's work out Gauss constraint, and it's going to be related to um, the before I claim that the Ashtekar A, this Ashtekar this A variable is a gauge connection. It is a gauge potential, but I need to tell you why we say this is a gauge potential and why we say this is a gauge potential with gauge group SU2, and this is all related to Gauss constraint, right? And then the Gauss constraint should generate the gauge transformation of A, right? And it shows that A is really a gauge potential with the right gauge transformation. Okay, so let's work out gauge transformation. Gauge transformation. Again, so because this is, I'm not going to derive it, but I'm going to show you the result, and I leave it as a homework for you to do the exercise. I think it's better for you to work it out by yourself. But I'm going to give you the result and the key point. Gauss constraint. Again, so now the Gauss constraint, I smear the Gauss constraint equals to integral p3x I gi and well gi here. Gi is just the new covariant derivative defined by A. Okay. And you just apply the formula and compute the Poisson bracket, just like how to generate gauge transformation as before. You just use that to generate gauge transformation, and these I will call delta lambda A, AI. Okay, and well, even from inspection, you can see that this is Poisson bracket between A and G is just a covariant derivative act on E. Okay, and then what you do is just the integration by parts, moving this covariant derivative from E to lambda. So this is the scheme of the derivation. Okay, and then so which means well, this Poisson bracket is a functional derivative of A with respect to A is just a delta function. So which means the only thing non-trivial is the functional derivative of G with respect to E. Yeah? And then the result is just the covariant derivative act on lambda. Yeah? So from inspection, you should be able to roughly see the pattern. Of course, you need to work out in detail to justify the coefficients and convince yourself it is really the case. dA lambda I, okay? And this dA lambda I think is the following from beta partial A lambda I plus epsilon I j k A j lambda k. So this is the explicit expression for this dA. Okay, so this is the gauge transformation for A. So you can see that. So well, I mean, if you're familiar with gauge transformation for the gauge potential, you should be able to see that this is exactly the infinitesimal version of the gauge transformation for gauge potential. Okay. Yeah, I'm going to write down something more familiar with, for you, which is finite gauge transformation for A, but you should relate them. And similarly, you should be work out the gauge transformation for E. So this is just the E AI X Poisson bracket with Gauss constraint. And the result is minus kappa beta epsilon I j k lambda j Yeah, and the calculation is again very simple. You just expand, you just plug in the explicit expression for GI. So GI of course depend on A, and this Poisson bracket between E and G actually grabs the functional derivative of G with respect to A, and the coefficient of that term is just this result. It's a good exercise for you to do the functional derivatives, but well, since you have done previous exercises, I guess you should be familiar with that already. Okay, and then this is your homework to check them. And show this delta lambda A and delta lambda E is the infinitesimal version of the standard gauge transformation in gauge theory. Infinitesimal transformation of the finite gauge transformation EA. So here now AA and EA, they are matrices. Yeah? They are Lie algebra value. They are matrix valued. Well, give you explicit formula AA equals to AAJ. It also relates to our convention for Lie algebra generator. So I will call this is tau J. Tau J is a matrix, and tau J equals to minus I sigma J. Sigma J is a Pauli matrix. It is J equals to 1, 2, and 3 is Pauli matrix. All right, and so this is A, and E is similar. EA is also a matrix. So EAJ. Okay. So here we take the basis for the SU2 Lie algebra to be tau divided by half. So here tau J divided by half, 1, 2, 3 is the SU2 Lie algebra generator. So, well, at this point, you have to have some knowledge of group theory and Lie algebra. But unfortunately, in this class, I'm not going to introduce what is Lie group and what is Lie algebra. Well, but now you have to have this knowledge in order to follow the class. But we don't need to use very much about Lie group and Lie algebra. We only need the basics about SU2 group and SU2 Lie algebra, or SO3 group and SO3 Lie algebra. And for those of you who have learned Lie algebra in my quantum field theory class, and you are very lucky, you have that knowledge already. Okay, so what is the finite gauge transformation for those quantities? So this is given by this. This is G A G inverse plus G partial A G inverse. Okay, and G is a group element, SU2 group element, or and more precisely, G is SU2 group valued function, and E is just a conjugate. Okay, and so here, well, A is a field, right? And so here G is also a field. It is SU2 group valued function. Yeah, group valued function. Yeah. So all the gauge transformation are functions, right? So our gauge group value function. Just like, well, I mean, in electromagnetism, well, by gauge transformation plus chi, right? Chi is also a function. Chi is your gauge parameter, and it is also a function. Here it is. The simplest U1 gauge transformation, so chi is just an ordinary function. But now the gauge group is SU2 because you have indices I from 1 to 1 3, and so this gauge group is non-abelian. So yeah, you have a group value function. And your homework is of course check this Poisson bracket, and secondly, you should be able to check that the infinitesimal version of this finite gauge transformation is precisely these two guys, give you these two formulas, and you should be able to translate what the relation between G and this lambda. Yeah. All right, so a function, and this is called local SU2 gauge transformation. Okay. All right. So this is the well, this relation. So this relation convinces us that the gauge transformation for A and E indeed is the same kind of gauge transformation as in non-abelian gauge theory, as in the standard non-abelian gauge theory. At least a part of the gauge transformation. This is the gauge transformation generated by Gauss constraint. If you consider those gauge transformations, the gauge transformation for A and E, they are precisely the the same as the standard gauge transformation in a non-abelian gauge theory, where the gauge group is SU2. Of course, you have additional gauge transformation, which are traditional for generativity, which are diffeomorphism. Again, the so diffeomorphism constraint will just give you the same kind of gauge transformation as before. Just for diffeomorphism constraint, they just give you the diffeomorphisms, generate the diffeomorphisms on the spatial slice. And the infinitesimal version of that gauge transformation is just a Lie derivative. I x. Okay. And similarly for Hamiltonian constraint. Then we just give a Lie derivative. If you use equation of motion, well, and if you have done the previous homework, you understand what I mean. If you use equation of motion, you should get this is just a normal Lie derivative with respect to hypersurface. I won't give you homework for you to check them, because this is just a simple consequence from ADM stories. But do make sure that you really understand the ADM derivation. Yeah. And okay, so these two equals. So actually, you use equation of motion. Okay. All right. So these are the gauge transformation generated by constraint, and another thing I have mentioned that they are all first class. So which means that you can work out the constraint algebra, first class constraint. So firstly, if you compute the Poisson bracket between two Gauss constraints, So the result is still a Gauss constraint. Yeah. So here, this is the commutator between lambda. So here it means that this is commutator of these guys, lambda j tau j. Yeah. So here I consider lambda is also Lie algebra valued by consider lambda j is just coefficients in front of the Lie algebra generator tau j. This guy, and if you consider Gauss constraint with a diffeomorphism constraint, and the result is it equals to a Gauss constraint Lie derivative act on lambda. So this is just means that well, it just means that diffeomorphism generates spatial diffeomorphism. Diffeomorphism constraint generates diffeomorphism transformations, and it transforms the Gauss constraint. Yeah. So this equation is also very easy to understand. And the Gauss constraint with Hamiltonian constraint, you just get 0. This is 0. And well, the other constraint algebra is going to be more or less the same as ADM situation. And prime two diffeomorphisms still give you a diffeomorphism. Okay, and diffeomorphism Hamiltonian give you Hamiltonian. C. Sorry, so we have no vector here. C. Prime. This is prime. Okay, probably there's a minus, yeah, because I put a diffeomorphism constraint in front of the Hamiltonian constraint. So it is minus equals to minus of diffeomorphism act on Hamiltonian constraint. So you see, and this formula is also, you can understand, similar as the diffeomorphism Poisson bracket with Gauss constraint. Diffeomorphism just generate. Diffeomorphism constraint just generate diffeomorphisms, act on the function. Yeah, together. Well, act on the Hamiltonian constraint. So on the right hand side, you just get this result. You get Hamiltonian constraint get translated by Lie derivative. And then the Hamiltonian constraint with Hamiltonian constraint prime. Yeah, and again, you get, of course, the same result because they are the same constraint as ADM variable. That's C and D and prime. And and you will get some additional term, but those terms are not important at all because those are terms proportional to Gauss constraint. Term proportional. Okay, so that's a constraint algebra, and they are clearly first class because all those constraints, if you take any of their Poisson bracket, the result is still a constraint. So it means that they are first class. Okay, so now we finish the canonical theory of Ashtekar variable. So here I give you a conclusion is that now in terms of Ashtekar variable in terms of Ashtekar variable. Our theory, the theory of generativity, is reformulated as a gauge theory. GR is reformulated as a SU2 gauge theory with gauge potential AA. So the theory has a gauge potential, just like ordinary non-abelian gauge theory. But of course, you get additional constraint and gauge transformation compared to the non-abelian gauge theory, which are diffeomorphism constraint and Hamiltonian constraint. So the usual non-abelian gauge potential, the usual non-abelian gauge theory, you have only one constraint, which is a Gauss constraint, just like Maxwell theory. Electromagnetism, the constraint is just the Gauss constraint or Gauss's law, right? That's the only constraint you have for Maxwell theory. And for non-abelian gauge theory, you also only have a Gauss constraint. But here, for generativity, you have not only Gauss constraint, you also have diffeomorphism constraint and Hamiltonian constraint. And another difference is that for usual non-abelian gauge theory, you have a Hamiltonian, right? You have a non-zero Hamiltonian. But for generativity, you have your Hamiltonian, which is zero in the bulk, which is just a linear combination of constraint. Your Hamiltonian is just a linear combination of the constraint. And the only non-vanishing term is some boundary term. Here we have ignored boundary terms. Only non-vanishing boundary terms. That's the speciality of generativity. And thirdly, well, probably I should write it. Well, firstly, additional constraint, namely diffeomorphism and Hamiltonian constraints. And secondly, vanishing bulk Hamiltonian. Okay, and thirdly, the theory is background independent. Background independent. And the theory, this theory is clearly independent of any metric. So because generativity metric is a dynamical variable, and the theory of generativity is completely independent of any pre-assumed metric. Well, but the usual non-abelian gauge theory depends on the metric. So clearly, the Maxwell theory depends on the choice of metric. The background metric is a flat space. It depends on the metric. But here, generativity is independent of metric. So there are three differences. So here it is similarity with the usual non-abelian gauge theory, but here there are differences. This is from usual non-abelian gauge theory. into non-being gauge series. Okay, yeah. So, but anyway, we have cast GR into a in a formulation which is very similar to which is similar to non-abelian gauge theory, especially in terms of this new variable, this gauge potential A. So so then this is the idea that the quantization of the theory is getting easier because we have already a lot of tools to quantizing a non-abelian gauge series. Yeah, so we have already a lot of theories about quantization of non-abelian gauge theory, and we have all kinds of methods can borrow from ordinary quantum field theory, right? And we can apply those methods to general relativity and perform quantization, and that's the performing this idea. The result from this idea is so-called loop quantum gravity. So quantizing GR using method of non-abelian gauge theory okay, and the result is what we call loop quantum gravity. This is something I'm going to talk about the next lecture. So loop quantum gravity. Or in short, LQG. Okay, and yeah, we are going to talk about quantization, at least some further preparation of quantization in the next lecture. Okay, there is one thing I think I forgot to mention is that in general relativity, the Hamiltonian, the bulk Hamiltonian, is vanishing on the constraint surface, and so this is usually people call it the problem of time in general relativity. Yeah, so because you have no Hamiltonian, you have zero Hamiltonian, and the time translation is just a gauge transformation, which means in general relativity there's no sense of time. You just have no meaning of time. So then in the quantum theory, it caused some problem. Yeah? But yeah, we have to have some effort to avoid this kind of problem. So that, and also you can see that this is the difference between general relativity and any other field theory you have learned before. So before, in any other field theory, you also have a Hamiltonian, and the Hamiltonian generates time translation. But now for general relativity, for gravity, you have no Hamiltonian. Yeah? The Hamiltonian is zero on the constraint surface. Okay, so which means that it is very special. Okay. All right, I think that's all for today. I think next lecture I'm going to firstly talk about the boundary terms. Before I always ignore the boundary terms. I have to get it back at some point. So, but I will briefly talk about boundary terms next lecture, and then we come to the quantum theory. Okay. Yeah, that's all for today. And if you have some questions, probably it's a good time to ask. Okay, so if there is no question, then we can stop.